Hello everybody and welcome to section 3. We're finally going to talk about the driving mechanisms of plate tectonics. So first, this is approximately what the Earth looks like when we divide it into these plates, these different chunks on the surface. And we have a definition here for plate tectonics: movement and interactions of these plates, the big fragments, along with a number of smaller pieces, which are parts of the Earth's lithosphere, the hard parts at the outer edges of the Earth, things which move like rigid bodies. So we have our evidence from before that the plates do move, continents are moving, but how and why do they move? And we're going to review just a little bit here what the interior of the Earth looks like. So we have our inner core and outer core. These are real hot. These are providing our heat source, which ends up driving everything else. Pay attention, here we have the lithosphere at the top. So our crust, and then the uppermost part of the mantle, which is rigid and solid. And beneath it we have the mantle, which is mostly solid, but partially molten. And so it's able to move around. It's sticky. It can behave like putty whenever it needs to. And the mechanism we're going to talk about here for driving the motion of the plates is mantle convection. Example of this one is a lava lamp. So we have our heat source at the bottom of the lamp. This gets hot. Whenever it gets hot, density goes down and it starts to rise. And as it gets to the top, it loses heat, gets colder, then it starts to get real dense. It gets heavy and it sinks down to the bottom, where it gets heated back up again, which is why the lava lamp is in constant motion, creating this little cell. And the mantle of the Earth works the same way. So we have our internal heat at the bottom coming from the core, and this convection cell contains, we think, the entire mantle. So hot material from the lowermost parts of the mantle rises up to the top, circulates around, cools off, and then drops back down again. And here we have a diagram which sort of puts it all together. So we have a continent on one side, a continent on the other, our oceans in the middle, and what's driving the forces here ultimately are these convection cells in the mantle. So we've got our heat down here from the core, which causes hot rock to rise up. It gets here, it melts, and it is pushed outward as it solidifies. Once it gets back to the continent here, it gets old and cold and it sinks down into the mantle, down here where it gets recycled and then comes back up. You can think of these as being a little bit like conveyor belts or something at the grocery store, going around and around and around. And as it does, it pulls all of this above it, the continent and the ocean floor, with it away. Ultimately, the heat source for all of this is within the Earth, near the core. The technical way to put it is that plate tectonics is a mode of heat loss. It's the way that Earth is losing heat, this initial heat that it has. A planet like Mars does not have this sort of moving surface, in part because the interior of Mars is cold. Mars is comparatively a dead planet. So why is the interior hot? You might remember from one of the earlier lectures that Earth started out as being incredibly hot and has been cooling down, but why is it still hot? Why is it not all cooled down yet? Why are we not like Mars? There's a couple of reasons for this. So we have our three main heat sources. The first is our heat of accretion, our initial heat source. We have number two, this is from differentiation. This is our frictional heating. So as all the dense stuff that formed the core sunk down into the Earth, there's a tremendous amount of friction between it and the rocks around it, causing even more heating. And finally, heat from the decay of radioactive elements. So this is especially true for the outermost portions of the Earth. There are unstable elements up there which are constantly shooting off energy, and this energy that they shoot off in part takes the form of heat, causing the crust and some of the upper mantle to be heated. And this is what the sun might look like. So at the base we have the core, which is transfer heat outward by conduction. Just by touching something hot, you transfer heat. That's when we talk about conduction. And then we have convection cells operating here in our liquid outer core. And then we have big mantle convection cells, which ultimately are responsible for driving the motion of these plates, which we see at the surface. So just to summarize here, plate tectonics is the theory that Earth's outer shell is divided into several plates which glide over the mantle. Deformation of these plates is mainly concentrated at the edges of the plates and not the interiors. The interiors, you should be thinking of somewhere like Kansas, relatively stable, boring places, as opposed to the edges somewhere like California near Los Angeles. That is where the excitement is. Deformation is concentrated along the plate boundaries. And plate tectonics is, for all intents and purposes, the grand unifying theory of geology. This is the larger scale framework which all of the other smaller pieces fit into. This is something which the ideas of which were around for a long time, but didn't really gain acceptance for quite a while. A large part of this was, well, plate tectonics sort of invalidated the work of a lot of geologists which had come up till that point. Everybody's existing research needed to be, at the very least, modified, but even just thrown out entirely in light of this new idea. Part of the reason why we see, from the 1950s through the 70s, why did it take so long? Why did it not catch on right away? People were reluctant to abandon their old ideas that they had sometimes spent their entire lives working on. The driving force behind plate tectonics is convection in the mantle. So hot material near the Earth's core rises up. This is the up part of our conveyor belt. And then the colder mantle rock sinks down. This driving cell is what causes the motions of the plates above it. And we split this sometimes into other forces. We talk about pushing and spreading apart at the mid-ocean ridges. So this is the ridge push force, pushing the two plates outward, pushing them apart. Call this a divergent boundaries, where they move apart. And we're also talking about the sinking force. So this is the slab pull. Sometimes when we have two plates that come together, one of them will sink down beneath the other one, and as it does, it pulls the entire plate behind it with it. This is a convergent boundary. We're going to talk much more about the boundaries in the next unit.